This video we will be discussing about the LIPSI processor. Let us briefly try to understand what is a LIPSI processor. LIPSI processor is a 8-bit processor which is designed for minimal resource consumption. It is based on accumulator architecture, and when we analyze the memory, it has Harvard architecture. In Harvard architecture, the memory is divided into two blocks, one for the instruction and one for the data. Now let us try to understand how LIPSI works. LIPSI is a non-pipeline processor. As I said earlier, it uses a single block of RAM which stores both instruction and data, which is time-shared between them. Hence, it makes the process sequential, thereby making it a non-pipeline processor. And just like other processors, our processor also has a program counter, ALU unit, and an accumulator register. Now, let us try to understand what is an instruction set. I'll explain this with the help of an example. Let's say we need to add two numbers, a plus b. Plus is an operator and AB are operands. Now this we can understand, but computer cannot understand. So to make computer understand this, we need to convert this into a parameters or instructions which is predefined and which can be understood by the processor. So an instruction set is a complete collection of basic operations that a processor can understand and execute. This is the instruction set for the LIPSI processor, which is given by the Professor Martin, who invented this processor. And the encoding used is as follows. This is a crude data path for the LIPSI processor. It is not compulsory to follow this data path. We can follow some other data path also, but we need to ensure that we use the same instruction set and the same encoding. And how is our LIPSI processor different from a traditional LIPSI processor? As you can see that in instruction set we have some don't care conditions which give flexibility for the user to add his own instructions. So we added 4 extra instructions along with the traditional instructions to just increase its instruction set. Now let us see how we implemented LIPSI. So we modeled LIPSI processor as a finite state machine, and we use 16 states, which is basically 4 flip-flops. As you can see that for every state we enter a for every instruction we enter a default state which is fetch, and from there according to the corresponding instruction we enter a suitable state to execute the instruction and then return to the default state fetch. So in this way we implemented all the instructions, as you can see. Now let us understand why we need extra states. As you can see from the instruction set which is given above, the load indirect and store indirect takes one extra step because we need to get data from M of R, which will get in one clock cycle, and in another clock cycle we will get data from M of R and then assign it to accumulator. So we need one extra step for load indirect and store indirect. And for ALU immediate, it executes these instructions in 4 clock cycles. It is because in one clock cycle we will get the first byte of instruction, and in second clock cycle we get the second byte of instruction, which is essentially the data, and in third clock cycle we execute the instruction, and in fourth clock cycle we return to the default state, which is fetch. So we require a total of 4 clock cycles for ALU immediate and branch instructions. Now let us see this table which describes about the instruction set usage and its importance. You can just go through this table. Okay. This is a LIPSI schematic. We'll come to this later. Let's skip this part for now. And this is our power analysis for our processor. And this is our timing analysis. As you know that when we design a processor, the setup time and hold time violations are very important. Now let us see what are the limitations for this processor. As I said that our processor is based on accumulator architecture, so it's basically a simple architecture. Nowadays I guess no processor uses accumulator based architecture. It uses more complex architecture. And I said that has a non-pipeline execution, which basically decreases your speed. So it's a limitation. And another limitation is it has limited instruction set. As compared to other processors, this instruction set is very small. So these are the three limitations of this processor. And what you can do is, as a future works, you can just try to expand this. You can make from non-pipeline to a pipeline processor. You can expand this instruction set. You can add input output pins, etc. Now let us see how we realize this processor. I have used Verilog to realize this. We can also use system Verilog. So let us use divider tool, which is given by Xilinx. So to make this LIPSI processor, first I made this clock divider module. It is because I at the end of the day I want to dump this on an FPGA, and for a basis 3 board it has an inbuilt clock of 100 megahertz. So to observe the output on the 7 segment display or LEDs, we need to decrease the clock speed to 1 hertz so that we can see the output. So I made a clock divider which decreases it to 1 hertz. I made another clock divider which decreases it to 1 kilohertz. This is basically for the 7 segment display. Now this is our main module, which is finite state machine. So which takes the input clock and reset. Outputs are accumulator, the PC, and this is just an output flag to ensure that we executed the instruction successfully. So first I declared a global parameters to assign the states and encodings. So these are the 16 states which I used: fetch, store, indirect to, etc. We'll look into this detail later on. And this is a memory. So I have created a memory of 512 bytes, and I have just assigned the memory with some initial instructions. So I just want to display how the sum of 50 natural numbers. So these are some internal signals, and these are some temporary variables which I used. We'll see later on why we will use these variables. Yeah. So first thing I want to do is, irrespective of the clock, whenever the PC updates, I just want to fetch the instruction. So in an always block, I'll write this statement. Next, in the always block, if reset is given, I want to start the system. So I'll initialize the PC to 0. I'll initialize the accumulator to 0, and the default state is fetch, and the internal signals I'll all assign them 0. Now let's see else condition. That is, if there is no reset and passage of clock is detected. Now, if any this signal, as I say, internal signal, if it is 0, I want accumulator to be accumulator only. That is, I don't want to change the accumulator value. If I want to change this, I need to make this internal signal high. This display is just for the debugging part, so just ignore it. Now we use the case statement, and we'll switch the states, and we'll execute it accordingly. Now I have written first the fetch state. In fetch state, we'll basically fetch the instruction. So if according to the instruction set, as you can see, when 0 is detected, we need to perform the instruction ALU. So if instruction is 0, we'll go to a state which is called as ALU up, and we'll make the internal signal enable accuracy high. That is because we need to write the value of the result into this accumulator. So we made the signal high, and we'll go to a state called ALU up. And for that, As you know that ALU, it does the ALU operation between the accumulator and the M of R. First we'll just fetch M of R, that is memory, and the first bit 1 indicates it's a data. We use the ninth bit to differentiate between the data and the instruction. So we will just fetch the data from the memory, and similarly if instruction 1000 is detected, then we'll go to another state called store, where basically what does this, it stores the accumulator value into the memory. Here the accumulator value is stored into the memory, and when we detect 1001, we'll what we have to do is we have to assign the accumulator value to the PC, and PC value we have to assign to the memory. Here, as you can see, we use these temporary variables where we'll assign the PC value to a temporary variable and accumulator to PC, and we'll go to a state called brlink. Similarly, for every instruction, we'll go to the corresponding states like this. Now let us see in ALU states what we'll do. As you can see, I've already created this according to the encoding given in the research paper which is given by Professor Martin. I already declared this as parameters in the above. So I'll just add them and store them in accumulator. For subtraction, I'll just subtract with data, or operations, or operation, load, add with carry, subtract with borrow. And it is very important to have a default condition. And after this, as I said, I'll go to again a default state which is fetch, and I'll make the internal signal 0, because after writing into the accumulator, I just want to store the value, I don't want to write anything. And I'll increment the PC, and whenever this PC gets incremented, we fetch the next instruction, because we already made a always block above. And in store state will, as already we store the value earlier, like we executed the instruction earlier, so we'll just increment the PC and go to a state called fetch. As I said earlier, for load indirect we need an extra state. So first, before doing the instruction, like executing it, we'll go to another state which is called load indirect 2, and there we'll store the temporary value into accumulator, and in load indirect 2 we'll increment the PC and go to a default state called fetch. Similarly, store indirect 2 is also implemented, and in this way all the respective states are implemented according to this instruction set. This ALU immediate is where we do ALU operation between the accumulator and the data itself. Here the data is given by the user. We don't fetch it from memory, unlike like ALU register. So here we'll directly fetch it from the instruction, which is the program counter, and we execute the same ALU operations. So this is how we implemented the ALU immediate. And after it is done, we'll make the enable accurate 0, so that the accumulator stores its value, and we'll go to a state called data 3. From there again we'll increment the PC and we'll go to a default state called fetch. And in input output state, we just want to store the accumulator value into the output and the given input to the accumulator. So we have done that by using a temporary variable. We stored it into the accumulator, and the accumulator value we stored it into the output. After completing this, we incremented the PC, made the enable accurate 0, and then went to a default state again to fetch the instruction. This is the exit state. As I said, in exit state we'll just make the signal 0, we'll freeze the PC, and we'll make the output signal high to ensure that our code has terminated, like our processor has terminated successfully. And this is how we implemented ALU shift, where based on the corresponding encoding, we'll shift it as a left shift, right shift, and these are left rotate and right rotate respectively. After finishing this, we'll again go to a default state called fetch. it is very important to write the default statement, don't forget it. And in this is how we implement the branch state, where we'll we'll just increment the PC to get the address. It is to where we jump, it is basically 2-byte instruction. So we'll increment the PC and get the address, and based on that address we'll branch. In this we'll go to a state called branch, and in that state, based on the encoding, we'll branch. If accumulator is 0, we'll branch. Else if accumulator is not 0, we'll branch. So these are the corresponding encodings, like as you can see here. Branch if a is 0, branch if a not 0. Based on the corresponding encodings, we'll branch. So we completed the finite state machine module, and we needed top module. So this is basically a top module which has the input clock reset, and the output is a 7-segment display. For the 7-segment display, we also need a anode pin, since base history board is a common anode, and this is the output pin. As you can see that we divided the internal 100 megahertz clock to 1 hertz, and we gave this 1 hertz clock to the processor, and this 1 kilohertz clock to the 7-segment display. And this is basically the 7-segment code, just the 7-segment code. That's all. And this is the test bench for the LIPSI processor, where we tested our data path module by just giving some clock and giving initial reset condition and just removing it and observing after 3000 nanoseconds. Now let us see the simulation. Okay, as you can see that our code executed successfully. You can just zoom it and see the sum of 15 natural numbers 6 just printed. We'll just go to the last. Yeah, now it's correct. We got the sum of 15 natural numbers, which is 78. Here 78 is in hexadecimal. If we convert to decimal, it is equal to the sum of 15 natural numbers. And as you can see, the output is high, which means the code successfully terminated. And this is the PC values. You can just zoom in to see the in between values. You can just zoom in. You can just zoom in to see the intermediate values. So you can see the PC values, the accumulator values, and we have dumped this on bus history board also. It's working perfectly. So this is how we implemented a LIPSI processor. Okay, guys. Thank you so much, guys, for watching this video.